Welcome back to section 2 of chapter 8. In this section, we're going to be looking at lHpitals' rule, which takes us back to limits. A lot of times, this topic falls back in the chapter when we're first looking at derivatives, but here it comes way at chapter 8. So lHpitals' rule was named after some guy, Willem de lHpital. lHpital's not his last name, it's where he lived. Anyway, he was a nobleman who published the first calculus book and really contributed a lot to math and science. Not so much in and of himself, but he hired a bunch of mathematicians, which allowed them to work and make discoveries and stuff like that. So um, he was a good supporter of the maths and sciences, like maybe the first STEM person. And so the first thing before we get into it, though, lHpitals' rule. Sometimes lHpital is spelled like that. Sometimes you'll see it spelled like this. So it's always pronounced the same, but the O with that weird triangle accent over it could be replaced with an OS. So it's lHospital's rule. It is still pronounced lHpital, though.
And so what is lHpitals' rule? lHpitals' rule says that if you have two functions that are differentiable on an interval, now this does not have to be a big interval. It just means that it has to be differentiable right near this one little point, except possibly at the point itself. And the g prime of x doesn't equal 0, except possibly at that point. And there's lots of hypotheses in this part, or lots of conditions. The limit is x goes to c of f of x over g of x equals 0 over 0. So we have a fraction going on here. It equals 0 over 0 or infinity over infinity. Then the limit as x goes to c of f of x over g of x would be the same as the limit as x goes to c of f prime of x over g prime of x. So what that means is we can take the derivative of the top and the bottom separately and then find the limit of that, and that'll be the same thing. We'll see why that works on the next slide, but first let's see what this is actually doing. So let's do a problem, one that we've actually seen a few times. The limit as x goes to 0 of sine of x over x. We saw this when we were looking at the derivatives of sine and cosine by the definition in the very beginning. And I said that you're just going to have to trust me on what this limit equals at the moment. We could look at it under calculators and see visually that, okay, I wasn't completely out of it. But here we could actually find the limit. And so we have the limit as x goes to 0 of sine of x over x. The very first thing that we have to do is we have to plug in that number because it needs to equal 0 over 0 or infinity over infinity. If it does not equal one of those two things, lHpitals' rule does not work. So we plug in 0 over 0. We get sine of 0, which is 0 over 0. It's nothing really going on. So we have 0 over 0, so we have to do something else. We're going to use lHpitals' rule. The way I've always done it is I do the little L apostrophe H. It's my note saying I'm doing lHpitals' rule in this step. So what lHpitals' rule says is we can take the derivative of the top and the bottom separately. This is not a quotient rule problem. The derivative of sine x is cosine x. The derivative of x is 1. Then we can take the limit, the exact same limit we had. X goes to 0. Plug it in. Cosine of 0 is 1 over 1, which just equals 1. So the limit, x goes to 0 of sine of x over x, equals 1, which is what I told you it equaled before, but it's nice to see some verification. So that's the general how you use it. You take the derivative of the top, the derivative of the bottom, and you find the limit of that quotient. Couple big mistakes people make on this is one, they use the quotient rule instead of top and bottom. Secondly, when you go out and you're supposed to have a quotient rule problem, people try to do this. Now they've seen this. That doesn't work. These are two completely separate things. The other mistake people make on this is they don't check to see that it's 0 over 0 or infinity over infinity. And they do lHpitals rule on something that isn't meant for that, and it does not work. You will most often get a wrong answer, and the occasions where you get a right answer, it's pure luck and coincidence. So it's important to make sure that that happens. Generally speaking, the functions will be differentiable, and g prime of x won't equal 0. That's not something that you have to worry about too much unless you have this weird function thrown at you. Usually it's going to be a function that we know, so it's not a problem. Why does it work? We can look at the proof. So, for lHpitals rule, we have to have certain stuff has to be differentiable, doesn't equal 0, except maybe at c, and the limit of f of x over g of x equals 0 over 0. And so what that means is that we can add or subtract f of c and g of c, because if the limit as x goes to c of f of x over g of x equals 0, it means that f of c equals 0 and g of c equals 0. Technically, it doesn't mean that. It means the limit as x goes to c of f of x equals 0, which we saw anyway. It means that f of c equals 0 for all intents and purposes. We're putting it into another limit as x goes to c. It works for what we're doing. It's not perfect, but yes, for what we're doing, it does work. So f of x minus f of c, that's f of x minus 0. We can add and subtract 0 from whatever we want all day long. So we have that. The next step, we're going to multiply both the top and the bottom by x minus c, 1 over x minus c. So we're going to have our f of x minus f of c over x minus c, and then g of x minus g of c over x minus c. Now this should start looking a little bit familiar. We have y minus y over x minus x and a limit of it. That's a derivative. Specifically, remember we have that extra definition of a derivative that says the limit as x goes to c of f of x minus f of c over x minus c equals the derivative specifically at c. This is one that we don't use all that often. It's not quite as useful in a lot of cases, but it does come in useful here because we can see that we're pretty much there on both of these guys. We just need to split up the limit, which we can do, it's quotient. And then we have the derivative of f of x over the derivative of g of x. And so the limit as x goes to c of f of x over g of x equals the limit as x goes to c of f prime of x over g prime of x. But again, very, very important here, they do have to equal 0 so that those equal 0. If the limit does not equal 0 over 0, this doesn't work. It could also equal infinity over infinity. The proof is slightly different, but still basically the same. So that's why lHpitals rule works. Um, Next, we're going to look at a few examples of lHpitals rule because weird stuff can happen. It looks like, oh, it's just going to be super easy. And a lot of times, yes, it is. But sometimes you have to force it into the right form. So, before we have to force it into the right form, though, we have this one, limit as x goes to infinity of e to the x over x squared. We could plug in infinity. If we do e to the infinity is, well, that's just infinite over infinity squared is infinite. Hey, we have infinity over infinity. We can use lHpitals rule. So we're going to take the limit as x goes to infinity of the derivative of e to the x is e to the x over derivative of x squared is 2x. All right, then we can plug in infinity. E to the infinity is infinity over 2 times infinity is infinity again. We took lHpitals rule, but it didn't do anything. It did do something. Notice you started out with an x squared, now you have a 2x. What do we do now? It's infinity over infinity. Let's do lHpitals rule again. Yeah, you can do it twice in a problem. You can do it as many times in a problem as you need until you get either um, to an actual proper limit, or you figure out that it's not going to go anywhere. lHpitals rule is not going to work. An example of that is if you would have like sine over cosine. It's just going to keep alternating. It's never going to really change. And so lHpitals rule is not going to help you out too much on that. Although sine over cosine won't equal one of these, so you wouldn't use lHpitals rule on that anyway. So lHpitals rule again, we have the limit as x goes to infinity. E to the x is still e to the x over 2. Plug in infinity, we get infinity over 2, which is infinity or no limit. And so we have e to the x is getting bigger than x squared significantly faster, which you've been hearing for a few years now. E to the x, an exponential function, is the fastest growing function that we have. Logarithmic functions are the slowest growing functions. They still grow, it's just very, very slowly. So e to the x is going to grow way faster than x squared, and so it's going to tend to infinity. It's not going to slow it down. So that would be using lHpitals rule more than once. It's a possibility. Next one, we have some different forms. So if we have a form infinity minus infinity, such as the limit as x goes 0 of 1 over natural log of x plus 1 minus 1 over x, if we plug in 0, we're going to get 1 over 0 minus 1 over 0, which would be infinity minus infinity. How do we deal with that? It's not L'Hopital ready. Well, if you have infinity minus infinity, my first step would be to write them as one fraction. Because for L'Hopital to work, we have to have something over something. And so if we write them as one fraction, we might be able to get there. So, to write them as one fraction, we needed a common denominator. So we multiply by x over x here, multiply by the natural log over natural log there, and we get our fraction, which now it's 0 over 0. We can use L'Hopital's method now. So we find the derivative. Notice the denominator did require a chain rule. And we get 0 over 0 again. So we're going to have to use lHpitals rule again, probably. But right now, this is pretty ugly. Let's clean it up a little bit. Multiply both the top and the bottom by x plus 1. And so what that does is it'll cancel out the fractions. So we'll only have the big fraction. We'll have fractions inside the fractions. And in the numerator, we get x plus 1 minus 1, which those cancel. Denominator is a little bit tougher. But we could plug in 0. We get 0 over 0 again. So we're ready to lHpital it. When we do that, we're going to get 1 over stuff. Let's see, x goes to 1. Power or product rule on the natural log again. One of them is x plus 1 over x plus 1. That just reduces to 1. And the natural log of x plus 1, we can plug in 0. We get 1 over 1 plus 0, which is 1/2, which means this original equation or expression has a limit that equals 1/2. So we ended up using lHpitals rule twice after forcing it into one of the proper indeterminates, and lHpitals rule twice, and we were able to do this. Next one, what if it's 0 times infinity? So infinity minus infinity, what is that? In this case, it happened to be 1/2. 0 times infinity, well, 0 times anything is 0, but times infinity, what's that going to be? Again, it could be anything. It could be infinity. It could be 0. It could be anything in the middle. It could be negative. So, first step, we'd plug in infinity. We get 1 over infinity is 0. Natural log of infinity is infinity. So you have 0 times infinity. Write it as a fraction. Natural log over x instead of 1 over x times natural log. That's an easy one. Some of the tougher ones to write as fractions involve trig, where you might have like cosecant of x times something. Remember, cosecant is 1 over sine, and so it makes it a little bit easier. So, wrote it as a fraction, get infinity over infinity. We can lHpitals it. Derivative of natural log of x is 1 over x. Derivative of x is 1. Plug in infinity. We'll get 0 over 1, which is 0. So in this case, 0 times infinity equals 0. And then one more. What if we have an exponent? A few of these would be 1 to the infinity. 1 to the anything is 1, but what if it's 1 to the infinity? Infinity to the 0. Anything to the 0 power is 1, but infinity to the 0. And then 0 to the 0. 0 to any power is 0, but anything to the 0 power is 1, so what's that one going to be? And again, any of those could be anything. The rules do not apply. So we're going to find the limit as x goes to 0 from the positive side of sine of x to the x. So anytime we have an exponent like this, we're going to take the natural log of both sides. But right now we don't have a both sides to take the natural log of. So we're going to set up an equation. Well, first we get 0 over 0, but then set up an equation. Y equals sine of x to the x. Natural log both sides, and we get natural log of y equals, the exponent can come down, x times the natural log of sine x. It's still not going to get us 0 over 0 or infinity over infinity, but this x can go into a denominator. And now, if we plug in 0, we're going to have natural log of sine x. Natural log of 0 is infinity. It's actually negative infinity. That doesn't matter. And then 1 over x is also infinity. In this case, notice the domain was limited, and that's specifically because you can't have the natural log of a negative number. So we have infinity over infinity now. We can take the derivative. So we can use lHpitals method. So natural log of something is 1 over something times the derivative of something. It's 1 over sine times cosine of x. 1 over x is just x to the negative 1. So that'll be negative 1 times x to the negative 2. And now plug in 0 again, and we get infinity over infinity yet again. Well, let's simplify a little bit. The sine, the 1 over sine, that can go to the denominator. And this x that we put down here can go back up to the numerator. So we get the limit as x goes 0 positive of negative x squared cosine x over sine x, which if we plug in 0, it's always good to check, it's 0 over 0. So we can now lHpital it again. And when we do, the numerator has product rule in there. So we get negative 2x cosine x plus x squared sine x, then over cosine x, the derivative of sine is cosine. Then plug stuff in, we get 0 plus 0 over 1. So the limit of natural log of y equals 0. But that's not the limit we were looking for. We have to untransform it. So we want just the limit as x goes 0 of y, which means we'd go e to a power. E to the power of the natural log of y equals y. E to the 0, which was what the limit was, equals 1. So our original limit is x goes 0 of sine of x to the x equals 1. Now when you're doing this, if you do have the option of using a calculator, so for instance if it's not on the chapter test, I would graph the original function so that you have an idea of what you're looking for. You may or may not be able to tell exactly what it is right off the bat, but you'd know if it's 0, infinity, or something else. And so having an idea, an estimate, can be a very, very useful thing to have in some of these problems because they can get kind of hairy. Anyway, today you're just working on lHpitals rule. It's not this and a couple other things, it's just lHpitals rule. So keep working problems, keep asking questions, and as always, happy mathing.